Welcome everyone, I'm Murat Bilgencantes. Today we present our smart home integrated earthquake early warning and safety system. This is a collaborative effort. Kübra handled testing and integration, Cheval managed the hardware, and Elif developed the user interface. As the system engineer, I focus on the joint architecture and embedded TinyML development. Earthquake triggered deadly secondary hazards like fires, floods, and gas leaks. Current systems fail when the networks collapse and have dangerous communication delays. We solve this with an offline TinyML framework on ESP32H device. It analyzes accelerometer data, detects P waves instantly, ensuring zero latency response. Our main engineering requirements with offline stability with local processing and total response latency under 2 seconds. To achieve this, we chose embedded deep learning over simple thresholds to minimize false alarms. We use contactors and solenoids for immediate physical isolation. Looking at our level 0 design, ground motion inputs are processed to output immediate utility cutoff actions. Here you can see our decoupled architecture. Critical decision making is isolated from the user interface to ensure low latency. Finally, in level 2, the H unit directly triggers solid state relays to physical shut-off, gas, water, and power. Supported by our UPS backup, the system guarantees safety even during the total grid failures. Thank you.
Hello, I'm Kübra Dici. I'm the system engineer of the team. I will explain the implementation process of our project. Starting with the hardware implementation, we utilize an ESP32 microcontroller paired directly with a high precision accelerometer. For physical safety, we integrated industry solenoid valves and a dedicated UPS backup. For data sourcing, we initially trained our algorithm on nearly 35 gigabytes of global seismic waveforms from the state dataset. Then we fine-tuned the model using approximately 5 gigabytes of raw records from the AFAD and Candili networks. We enforced a strict 50-50 balance between real events and ambient noise. To prevent domain bias, our negative noise data was extracted directly from for-event quiet windows. In real time, this data streams through a 6-step DSP pipeline. This converts the raw signal to G-force, filters out gravity, and normalizes the data to prevent false amplifications. This data is evaluated via a 10-second sliding window, capturing exactly 2 seconds of silence prior to the P-wave arrival. By optimizing our architecture to utilize the ESP32's internal SRAM, we slashed our inference time from over 35 seconds down to just 380 milliseconds. We further concised the model, shrinking its memory footprint by 89% without sacrificing detection accuracy. Our trigger logic is strict to prevent false alarms. The system demands consecutive threshold confirmations. To validate this in real world, we custom built a 3D printed shake table driven by a stepper motor. By rapidly oscillating the platform, we accurately simulated dynamic ground motions.
Hello, my name is Nadia Shevalatish, and now I will be presenting the tests and methodologies, the performance validation of our artificial intelligence model, and how our final prototype successfully meets the engineering and safety requirements. So to evaluate the real-world performance, we divided our data into 3 parts. One of them is used for training, one of them is used for validation, and one of them is used for testing. After we used the test data for testing our system, we are met with these graphics. From there, we can see that our system detects actual earthquake signals around 92% correctly, and it is resistant to noise around 93%. If you look at the confusion matrix and the error analysis, we saw that out of 152 actual earthquake signal, our algorithm correctly identified most of them, missed some, but overall our model is highly evident. Also, we determined the threshold from these tests, which is 0.32. Here on the right is our interface, and on the left is our real-time notification. Here is a photo from exhibition, all of the parts connected together. So if we move on to requirements compliance, we acquired high classification accuracy, fast response latency, power resilience, and seismic sensitivity. Also, our hardware is low cost, assures high safety, integrated to smart home, easy to install, and have real-time notifications. So if you look at the complete picture of Edge Earthquake Early Warning Framework, we have transferred the rigorous data from Stat, which we used to train our model with. We have hyper-optimized AI, works around 380 milliseconds latency, also totally independent from outer power, and also physical safety parts, which is autonomous solid-state relays and solenoid valves. Thank you for listening.
Hello, I'm Elif Uygun, and today I will talk about our project's cost analysis, commercialization, standardization, certification, safety aspects, and lastly multidisciplinary aspects. After validating the technical performance of our system, we also evaluated its commercial feasibility and compliance with international standards. The total production cost of one commercial unit is around 5,146 Turkish liras, while the planned sales price is 10,000 Turkish liras including VAT. Based on our calculations, the project reached the break-even point after approximately 13 units, which demonstrates strong commercial potential. To ensure reliability and safety, the system was designed according to international standards, such as IEC 60364 and EN 61000 for electrical safety and electromagnetic compatibility. Since the ESP32 uses wireless communication, the design also aligns with Radio Equipment Directive requirements. In addition, the gas shut-off system considers ATEX safety regulations to prevent ignition risks in hazardous environments. User and environmental safety were also major priorities. After an emergency shutdown, utilities remain locked until the user manually confirms that conditions are safe through the smart home interface. Furthermore, all valve systems operate with low-voltage 12-volt DC power to reduce electrical risks. Another important advantage of our platform is offline autonomy. Because the TinyML model runs locally on the ESP32, the system can continue operating without internet access. Combined with the UPS and backup power bank, the platform can actively monitor and protect the environment for at least 6 hours during power outages. This project supports SDG 9, 11, and 13 by improving resilient infrastructure, urban safety, and disaster preparedness through AI-based autonomous protection systems. Our project also has a strong interdisciplinary dimension. From the computer engineering side, we developed and optimized the TinyML-based 1D-CNN model and created the smart home dashboard interface for real-time monitoring. In electrical and electronics engineering, we designed the hardware architecture including the MEMS sensor, ESP32 controller, relay systems, and power management units. Mechanical engineering contributed to the development of the physical check table and the integration of the valve mechanisms, while civil engineering knowledge was used to better understand real earthquake behavior and structural vibrations. By combining all these disciplines, we created a complete smart earthquake safety system capable of real-time autonomous protection. Thank you for listening.